Welcome to another video looking at HSC chemistry water testing, and in this one we're going to be looking at dissolved oxygen. So dissolved oxygen is the amount of oxygen that dissolves in water. Now if you remember with the oxygen molecule, it is a linear molecule and it therefore does dissolve in water, but remember it only has weak dispersion forces. So in order for aquatic organisms to respire and have that oxygen to respire, they need to have a certain level of oxygen in the water. Otherwise, they're going to undergo respiratory distress. So dissolved oxygen is the measurement of how much dissolved oxygen is in the water. Now, if we're looking at numbers, then we can say that less than 5 parts per million, the aquatic organisms start to have distress, right? They start to have respiratory distress. If we have, like 2 to 4, then we know it's polluted. And if it's less than 1, we can say they're dead. Okay, so we want a higher oxygen, dissolved oxygen concentration. Sometimes that's referred to as just the DO. Now, what affects DO? Okay, using the lingo. What affects it? Well, turbulence. Right, so the turbulence of the water. So if water is constantly in motion, like let's say the ocean, and the waves are going like that, it's going up into the air and it's hitting, coming down, it's dissolving, making a lot of bubbles in the water, and therefore dissolving a lot of water. So the concentration of dissolved oxygen at the surface of the water, if it's turbulent, then it will be high. As you go down into the water column, it decreases with depth. Okay. Temperature is also a factor. So as you know, if you increase temperature, that decreases the dissolved oxygen, right? So as temperature increases, dissolved oxygen decreases. And so the warmer the body of the water, the less dissolved oxygen there. I was reading the other day that there is I can't remember the exact location in the outback in Australia, but there's been a lot of farming in a particular community there and a lot of runoff, and that runoff has increased the turbidity levels of the lake significantly, and that coupled with a lot of evaporation of the water means that the water body is very, very warm. And I think they said just on a normal day when they measure it, it's close to like 30 degrees or so. And so that means that there's not very much dissolved oxygen in the water at all, and therefore the aquatic animals would be dead. So it's very important that we get the water body's temperature is at the right range so that it can have a lot of dissolved oxygen in there. If we have solute concentrations, okay, so if you remember in a previous video we looked at total dissolved solutes, that can affect the amount of dissolved oxygen as well. And then of course we have pollutants. If there's photosynthetic plants or photosynthetic algae in there, that's going to increase the concentration of dissolved oxygen. However, if we have too much algae in there, then we can lead to something called eutrophication and algal blooms, which then decreases oxygen. So dissolved oxygen is very, very important. So how do we measure it? Well, let's go over to our flow chart, the DO chart, dissolved oxygen chart, and we have digital probes. Hope you can hear that truck going past. Okay, and then we also have titration. So the data oxygen probes are very quick, easy, portable, and they can give you a nice value there. However, titration, it's a lab technique, and it's a technique called the Winkler method. Now this titration here, the students in HSC chemistry are not expected to remember it. However, there was a question in a previous HSC that gave you the steps in the Winkler method. It's a multi-step process. So they gave you the information, gave you the equations, and then you had to do calculations from that. So in the next section, I'm going to write all the stuff up on the board here, right? The board being the pane of glass, right? If you haven't worked out how we do this. I'm going to write it up. So you've got all the information there. Remember, you're not expected to know it, but you are expected to be able to do calculations from it. Okay, I'll write it, get busy, and I'll see you in a sec. All right, get ready for your retinal cells to be hyperstimulated because we're going to blow some brain cells out of your head. Remember that the HSC chemistry students, you don't have to memorize these equations. Because there has been a previous question asked on this where they gave you the equations, that's why I'm going through it, and so that you won't freak out. That's right, freak out when you get to an exam. So step 1 is when you've got the oxygen here. The oxygen will oxidize manganate ion to 4+, right? So it's going from 2+ to 4+. Step 2 is when you add some acidified potassium iodide, which reduces the manganate ion and also reduces the iodide ion to iodine. Then the last step is when we have to measure how much iodine is produced by titration. So this is a titration step, this one here. Right, that's the titration step. So you have your water sample, you add your manganese compound with acidified potassium iodide, and that all happens in the beaker, in the conical flask. Then of course you get your sample out with your normal titration, put it in a burette, etc., and you're going to be adding some thiosulfate to that, right? Some sodium thiosulfate. Now of course we've got to notice the colour change, so we put a starch indicator in there. But let's have a look what's happened. We've produced some iodine, so we want to measure how much iodine is produced. Right, so we add our thiosulfate and that reacts with the iodine to produce some iodide ions. Now I'm just going to rewrite these equations out here and add them together and see what the overall reaction is. And it's only the overall reaction you really need to understand when it comes to doing calculations, right? So if we write the first one out, so we've got 2Mn2+. And I might just speed this up just so you're not sitting there watching me rewrite an equation. And we're back. All right, so now we're going to add these together. And so we've got 2 manganate ions on this side, but only 1 on that side. So really we've got to times this by 2. So that becomes 2. This becomes 4 now. This becomes 8. That becomes 2. That becomes 2. This becomes 4. All right, so those are going to cancel out. And let's have a look at what else we can do here. All right, so let's cancel those out. Out they go. Now we've got some manganese dioxide here. We've got 2 of them now and 2 up here, so we can cancel those out. All right, and let's have a look at some iodine. We've got some iodide ions here. We've got 4 there and we've got 2 there. And we've got 2 iodines. We've only got 1 iodine here, so let's times that by 2. So put a 2, whoops. I've already got a 2 there. Let's just get rid of that and put a 4. So we've got a 4 there. We've got a 2, we've got a 2, and we'll change that to a 4. So now we've got 2 iodines. Let's get rid of that. All right, and let's have a look here. We've got 4 iodides here and 4 iodides there. They cancel. Now we've got 4, 5, 6 waters. So let's have a look there. We've got any waters on this side. We've got our 4 hydroxides there. Okay, so what we can do is, if we remember that the H plus and the OH minus can go together to make water, so let's take 4 of those across, right? That's going to give us 4 water molecules, right? And so that means those 4 waters there are going to get rid of those 4 waters. And I forgot to do a 2 there because I've times the whole thing by 2. Forgot to put a 2 there, all right? Which I think came from over here. Yeah, needed to be a 2 there, all right? So we got our 4 from here. That made 4 waters. We cancelled 4 waters. So that means instead of having 8 now, we've only got 4 of these. So let's add them up. What have we got on this side here? We've got our 4 thiosulfates. What else have we got? We've got our oxygens. Then we've got our product here. What else have we got? And we've got waters. 2 waters. Okay. So what does that tell us? Well, now that we've got this final reaction here, it says that 4 moles of thiosulfate will react with 1 mole of oxygen. So since we did our titration with thiosulfate, right, because remember we put thiosulfate to work out how much iodine was there, so we know how much thiosulfate we add, because of course we know the concentration we add and the tighter volume. We can work out the number of moles, which then allows us to work out the number of moles of oxygen. So I'm going to rub this out. Okay, we're going to write up some calculations and do a sample calculation, and we'll rewrite this so we can see the overall reaction. Be back in a minute. All right, and we're back now. All right, so I've rewritten that, and I'll put the equation up there, and I think just remembering back, I can't check because I've rubbed it off, but you guys need to note that. When I wrote the final equation down there, I think I forgot to put the 4 H pluses. So when we added the left-hand side up the top, we had the thiosulfate and we had the oxygen, but we also remember we had 4 H pluses left over from the 8 that were originally there, so we need to put that down on the reactant side, and so I've just popped that there. All right, so here we have it says 100 mils was taken from a lake. It was sealed and analysed. So when you do this, of course, you need to seal it because we want to measure the dissolved oxygen. We don't want to carry our sample around in the atmosphere where it can absorb more oxygen or lose oxygen if there is any organisms in there. So we seal it, and then we analyse it. And it says that we had a 0.01 molar thiosulfate. So if I just rub this molar ratio out, because we can see it on the equation, let's write what we know. And I'll use a different colour. So we've got 0.01 molar. It said we needed 9.6 mils to reach the end point. So 0.0096 litres. Okay, and now we want to work out the number of moles of our oxygen. So like any titration now, we do the same thing. We would say moles of thiosulfate used is equal to concentration times volume. Concentration 0.01 times the volume 0.0096. Okay, and that's 9.6 times 10 to the minus 5 moles. Okay. So that is in moles. We want to work it in terms of parts per million. Remember that milligrams per mil is equal to parts per million. So of course we want to now make this a mass value. So therefore we can go the mass. All right. Well, first of all, before we even do that, getting ahead of myself, we have to work out the number of moles of oxygen. So remember, this is the number of moles. So we've got 4 to 1 ratio. So we have to divide by 4 now. So the moles of oxygen in the sample is the number of moles divided by 4, which is 9.6 times 10 to the minus 5 divided by 4. And if we do that, it's 2.4 times 10 to the minus 5. Now that we've done that, we can convert it to a mass. Okay, so the mass of oxygen is equal to the number of moles times its relative atomic mass. So we've got 2.4 times 10 to the minus 5 times the atomic mass. Now remember it's O2. So 2 times 16 is 32. And so we're saying we've got 7.7 times 10 to the minus 4 grams. And that's the same as saying 0.77 milligrams. Okay. Now remember, that was in our 100 ml water supply, so we're saying 0.77 milligrams in 0.1 litres. So we divide both sides by 0.1, and so we get 7.7 milligrams in 1 litre, which is 7.7 parts per million. So we know that the healthy lake is healthy if you have 6 to 8 parts per million is healthy. 7's right in the middle of that, so this sample was from a healthy lake. So that's using the Winkler method. Okay, let me reiterate again that you do not need to know all those equations in the HSC, that is. However, you do, if you're supplied with the final equation, all right, you can still use that like any titration question and get an answer and then just convert it to parts per million down the bottom. So don't freak out too much, it can be done. All right, hope that makes sense. See you in the next video.